So this work I'm going to present now, it's 3D targeting over the Chisel Basin, and it's the culmination of all of this work that I just presented. That was a joint effort between Hudbay and Bruce and Mira Geoscience, and basically we worked with Bruce and also with Kelly Gilmore at Hudbay to develop a 3D grid, 3D targeting box set using all of this data that was compiled, or a subset of this data that was compiled, and developed a set of exploration criteria that were suitable for district scale exploration, and then did 3D targeting. So I'm going to just show you the process that we went through and some of the results from that. First, I'm going to introduce the project, and then I'm just going to show you, give you a bit of background on the weights of evidence analysis that we applied for targeting, and then show you what data we brought into the model to use for targeting, the list of exploration criteria that we developed, and then into the training cells that we used for the weights of evidence analysis, and the evidential layers that are the actual layers that we end up targeting on. There were 3 different targeting models that were completed, and I'll discuss that when I get to that point. And then I'm going to compare those 3 models and show you just a few pictures comparing the results of the targeting with some of these other infill geophysical models that were completed. So the targeting project, the basis was that the abundance of the 3D exploration data from Hudbay Minerals' Chisel and Lalor properties presented an excellent opportunity for application of 3D multidisciplinary mineral potential targeting methods. Quantitative mineral potential modeling allows us to evaluate and process many layers of data in a comprehensive, efficient manner. And the end result is a 3D mineral potential model that's attached to a workflow that can be revisited and refined and updated as new data comes in or new ideas are formed. We used weights of evidence methods for targeting in the Chisel Basin. And so this is referred to as a data-driven 3D targeting. And you can also use a knowledge-driven 3D targeting methods as well, which are based on expert opinion and input, and where experts decide on weights and thresholds that should be assigned to different data layers, and those layers are combined, and weights are added to give you a mineral potential model. But we used a data-driven method because we had some existing mineral deposits in the area, obviously, and we thought we would model. We would look for cells in our model that were similar to those that represent the existing deposits that are there. The targeting workflow for GoCAD mining suite was used to apply this method, and weights of evidence have been used since the late 80s for 2D mineral potential mapping, and that's an example there on the side of the slide there, showing 2D mineral potential mapping at a regional scale in Nova Scotia, the Maguma terrain. And so we have several different evidence layers: geology, multi-element geochemical data, structural information. This is proximity to anticlines. And then this information is compiled or combined to give you a probability model. With all of the deep drilling and 3D information that we're acquiring now, advanced 3D geological modeling techniques that we have, and 3D inversion techniques, targeting can now be carried out in 3D. And when you target in 3D, then you have a model where you're better able to define the depths and shapes of targets, and that's going to help you better focus your exploration surveys and improve your survey design, and basically optimally orient your drilling. So weights of evidence. For weights of evidence methods, you require 2 pieces of input information. The first is training cells, So that's the grid cell locations of known occurrences of a specific condition. So in this case, it's mineral deposits. And you need your suite of evidential layers or evidential properties. So it's a list of relevant data based on the deposit model, which are indicative, the cause or the symptoms of that condition occurring. So rock code, geochemistry, structure. And the output of weights of evidence analysis is a posterior probability. And that value represents the combination of evidential properties weighted by their spatial correlation to training cells. Often, the result is actually not officially a probability model. And that's because we can't say that it's a probability if we don't have conditional independence between evidence layers. If there's a relationship between evidence layers or a similar relationship between evidence layers and the deposit or the training cells, then you don't have an official probability. It's negated. And so we often look at these models in relative terms. You get an output, and we call it a mineral potential model or a map, and we don't often refer to it as a probability map. We don't want to say there's 88% of finding Lalor here. That's dangerous too. So in the case, for an example, you might say sodium depletion and potassium enrichment, they might be two processes that are related to the exact same phenomena. So that would, they would not be conditionally independent. So this diagram here shows how we calculate weights using weights of evidence analysis for the different evidential layers that go into the targeting. So the first thing that you do is calculate a prior probability, and that's just the ratio of training cells, which are the black squares, to the total number of cells in the model. And so that's just saying what's the probability of picking any random cell in this model and finding a deposit. So next we look at the different evidence layers, and we use binary evidence layers. And we assign, we have a favorable zone, so that's, in this case, in this evidence layer 1 here, that's the red zone, and then we have an unfavorable zone or region. And we assign positive weights to the favorable zone and negative weights to the unfavorable zone. And we do this by looking at the ratios of training cells that are sitting in the favorable zone versus outside of the favorable zone compared to cells that do not have training data. So it's just a comparison of these numbers. And so for the example here, we have something that might represent, you can imagine a buffer around a fault zone. And then for evidence layer 2, you might imagine this to be, say, a density anomaly. And you can't actually see this very good here, but visually you kind of have the impression that there's a good correlation between, spatial correlation between training cells and the favorable region. And this is reflected in the weights that are then assigned to that. So we have something like 1.5 and plus 1.5 and minus 1.2. The second evidence layer, whoops, sorry, Dennis. You can see that, visually see that there's not as great of a spatial relationship between training cells and the evidence. And you can see that reflected in the weight. So there's a smaller positive weight in the favorable zone and a smaller negative weight in the unfavorable zone. And to calculate the prior probability or the mineral potential, you add the posterior probability, you add the prior probability, and you sum up all the weights for a particular cell. You do that for all the cells in the model. So here is the combined evidence layers and a cell that exists in where there's the intersection between the two evidence. You add the positive weights from each layer. And if you're off here and where you just have evidence number 2, favorable for evidence number 2, then you would just have the positive weight for evidence number 2 and the negative weight for evidence number 1. So it's not very complicated. So to back up a little bit, then you have to, well, prior to that point, you have to get to a point where you have this this binary cutoff. You have to determine what is your binary cutoff going to be. So here we had already picked some binary cutoff. You need to get to that point. For each evidence layer, you have to determine your threshold value. And the way this is done is by looking at contrast between the positive and negative weights. And we want to find the place where we have the greatest contrast between the positive and negative weights, because that means we have a lot of training cells in a small volume versus few training cells in a big volume. So we want to find that optimal point where we can say we have a good statistical break in the data. So to find that point, we use several different cutoffs, or a suite of cutoff values. And if I flip through the diagram there, you can see we have our training cells as a deposit. And then we test all of these different intervals and calculate the positive and negative weights for that interval. And at some point you find there's an optimal cutoff value where the contrast is high. So that's how we determine our cutoff, our binary cutoff. So with that, I'll take you into the Chisel targeting project and show you the data that we used. So the first data set was a 3D geological model, block model, where every cell in the model contains a lithology. We have a structural model, density model from gravity inversion, magnetic susceptibility model from magnetic inversion, ZTEM inversion conductivity model, and interpolated geochemistry from drilling. And there were four models, and the interpolated geochemistry was interpolated geochemical indices, alteration indices. The exploration criteria, we were looking for the occurrence of favorable felsic and mafic volcanic units, proximity to unconformities representing hyadite and volcanic activity, proximity to intrusive bodies which could act as heat sources to drive hydrothermal fluids, proximity to the chisel thrust, a potential structure controlling the location of mineral deposits, proximity to synvolcanic faults and fault intersections within hydrothermally altered zones. We're looking for broad-scale magnetite destruction, so a decreased magnetic susceptibility that would represent, or that would reveal that. High densities indicative of dense ore bodies, and proximity to electrical conductors. So then we had our data layers, but now we need to convert our data layers to the input layers that we're going to use for weights of evidence targeting. So we have a rock code that stays as is. We have every cell filled with a value. Distance to unconformity, so we just calculate that across the volume, the distance to that surface that's representing unconformity. Distance to plutons, distance to the thrust, distance to fault. So we calculate all of these distance properties. We have distance to fault intersections, so that might represent areas of structural complexity. And then we can input directly the magnetic susceptibility model because we're going to look for susceptibility lows. And we have our alteration index models. And we have a model that we created from the density model, which represents density highs in felsics, because we just looked for those high densities that are in the modeled felsic geologic units and removed other density highs, which might be basalt or mafic rocks. And then we have our ZTEM conductivity model. So two things to point out here. We have these interpolated alteration index models. And the interpolation comes from the alteration indices that were calculated down the drill holes. So this is obviously biasing us toward drilled areas. So you have to make a decision whether or not you want to include that kind of information. A lot of times we have a lot of downhole information, so we want to use this information, but then you have to kind of understand that there's going to be some biasing. So in the models I showed you, I did use these Krieged models, and just have to remember that we're going to upweight things near drilled areas. And this might be useful if we're looking for areas to drill that are nearby, so stepping out from our original, from our existing drilling. The other thing to point out is The targeting process we use requires data to exist everywhere, for all evidence layers. So it's because if we have data that exists in subvolumes, like for example our ZTEM conductivity model, then there's going to be holes in this model. It's not too unlike the alteration index example, but so we're going to have upweighting or downweighting in areas where we don't have data for that particular evidence layer. So in this case, the ZTEM conductivity model has a chunk out of it because there's a power line there. And if we want to use this layer as an evidence layer, then we're confined only to that volume for targeting. So in one example, we have that chunk taken out because we want to use conductivity. The training cells, we tried using the Lalor deposit and then the Chisel deposit and then compared. So these are the binary evidence layers that I was talking about, and these are plan view slices. And this is actually from the model where we used the ZTEM conductivity. You can see that big bite taken out of the model. So we have rock code. So this would be, the reds are highlighting those rock types that we thought were relevant with respect to mineralization. And then we have all of these other binary properties which represent, in many cases, some distance away from some feature. And you can get a sense, looking at these, how close of a spatial relationship there was that was determined using weights of evidence analysis. The broader these zones are, the less of a spatial relationship existed between that data and the training cells. It meant it took many intervals before we actually encompassed enough training cells to say there was some kind of relationship. And then these big broad zones, because there was a weak spatial relationship determined, they're going to have associated lower weights. So if we input this into the model, it's going to come with a low weight. It won't be very influential. But things like distance to unconformity, which turned out to be relevant spatially with respect to known mineralization, this is going to come with a higher weight. So you can see here, these are the inversion binary properties, susceptibilities, densities, conductivities, and then these are the alteration indices, and you can see that there's close spatial relationship, but then it was also derived from drilling as well. So the results, there's three results. Model 1 was built using Lalor as a training region and incorporating the conductivity model as one of the layers. So that's why we have it. That's why we have a break in the model there. And so you can see Lalor was targeted using Lalor. That makes sense. And but we also have some highs that are coming off of the edge of the Chisel deposit there as well. And in this, when we use conductivity as an evidence layer, we can't use Chisel as a training because there's no data that exists over Chisel. So we can just use Lalor as a training set. So you can see that there's a trend that exists between the two different deposits. And then peeking out on the southeastern side of Chisel, there are some high values as well. And then Photo Lake, there's some indication that there might be potential up there. And this is an isosurface representation again. So the blue bubbles represent the areas of the highest mineral potential. And then the red circles are some of the highest ranked cells in those regions. And then I just put here those particular evidence that were contributing most highly to these regions being targeted. And there were alteration indices were influencing it, and also conductivity was influencing. The second model, Lalor, was used again as a training region, and this time the conductivity was removed as an evidence layer so we could fill the model back in again. But it was not considered for this result. And the result is very similar to the last model, and it's because we're still using Lalor as the training cell, and we're still seeing the high potential regions coming out mainly as a result of the alteration and the conductivity. And then in the cross sections here, you can see that there's some, so this cross section heads towards Lalor, and you can see there's a connection. It's because that model thrust is in there, and that's one of the criteria. And then we've got a section here that's closer to the photo deposit, and you can see there's some connection between those as well. High potential cells are heading up towards photo. And again, these are the high potential regions that come from that model. So you can see some high potential areas extending to the north from Chisel. And then there's some high values in here that are pretty interesting. The third model uses Chisel as the training region. And again, we didn't use conductivity because we couldn't. When we use conductivity, Chisel is not encompassed in that data. And I thought, when I saw this, I thought this looked like a flaming guitar. It looked really cool. And it looks kind of like the other ones, but there is definitely more of a distinct trend between the Chisel and Lalor deposits. And again, we have this trend that goes from Chisel up towards photo, but unlike the previous models where there were some high potentials up in this area, it doesn't seem to be the case in using Chisel as the training region. And really the reason is because Chisel and Lalor aren't identical, and I'm sure the geologists and geophysicists know that. And so each of the deposits have different relationships to each of the evidential data. So we're finding cells that have the data most like representative of Chisel and Lalor. And in this case, the result looks different because it's based on Chisel. And this is, again, the isosurfaces showing high potential areas. And so the highest potential areas. So Chisel is pretty well targeted, of course. And then we've got the string that leads up towards photo, and then another package of high potential cells that leads towards Lalor. And then in this case, the evidence that were most strongly influencing the results were unconformities, the thrust, and some of the alteration indices. This is a comparison between the three different results. The results using Lalor as a training data set, and then the results using Chisel. You can see the differences. These are fairly similar, and then this is a little bit different. They're all sliced at a similar elevation. You can see here that there's less high potential above photo than if we were using Lalor as a training data set. And then these are all the combined isosurfaces representing high potential regions. So the blues and pinks are using Lalor as training regions, so they're similar, and then the green is using Chisel as a training region, so it's a slightly different result. Some extra high potential areas down to the southeast. So just to close, I want to show some, because we are limited to using evidence layers that cover the entire basin, and we have all of these infill data sets and models. The next step is really to start comparing to all of this other disparate data sets that we have and try to validate the model or come up with extra evidence that these high potential areas are valid. And so one of the examples here, this is the MT inversion result over Chisel North. And this green here is one of the high potential regions. And I noticed that there are some high conductivity areas in the sort of shallow parts of the MT model. And if you crank up the scale in the model, this always works. You see there's a sort of a deeper fuzzy conductor that sits with this high potential area, and that was not used in the targeting effort. And I thought that was interesting. But you can see I've included a picture here of the Krieg sericite, and this is that same blob, the conductor, or where we have high potentials, and this deep high conductivity area correlates with high sericite. This is again comparing with the Chisel MT conductivity, and this is looking east. You can see the orientation here, and so east of Chisel, there's some high potential areas, and there's some conductors in the MT model there. And again, I have the sericite index model with showing sericite increased sericite alteration index in that area as well. So maybe there's some influence from alteration on the conductivities. And this is a final example here showing DC conductivity inversion. And as I said before, these are more shallow results. And again, this is looking at those high potential areas that are deep and south of photo. And just kind of above that in the DC conductivity model is a conductor, a small conductor. And then comparing that to the chlorite, carbonate, pyrite alteration index, there are some high index cells in that area as well. So in summary, an abundance of data within the Chisel Basin allowed for an integrated quantitative 3D approach to targeting. Mineral potential model results show under-drilled areas of high potential occurring on trend with existing mineral deposits, as well as at depth near some of the existing mineral deposits. According to the data compiled at this scale in the basin, Lalor and Chisel have different signatures, and this is coming out of the weights of evidence analysis. And weights of evidence analysis helps us to quantify those spatial relationships between the evidence and the different deposits. So in addition to weights of evidence used in targeting, it can also help us to interpret geology and the deposits, the differences in relationships between the training sets and the evidence layer might help us identify key differences between the deposits that maybe we didn't realize before. Like, for example, why does one deposit have a stronger spatial relationship to sericite alteration? 2D and 3D mineral potential modeling analysis presents an excellent opportunity for the exploration team to sit together and talk about the deposits and what the exploration criteria are and why these deposits sit where they do in a particular geologic setting, and to plan effective exploration programs. Once the evidential data are compiled on a grid, like we did for the for this targeting project, that's really the hard part: compiling the data, organizing it, interpreting it, and bringing it together on a single grid. Once you've got that work done, it's easy to test various hypotheses. You can test different combinations of criteria and see how the results change. So I could easily go back in, take out any of the drilling derived information and test to see what the results look like. So you can remove things that you might think are biased or overly interpreted. And the results can be easily visualized, tested, and validated against one another when all the data are integrated within a single 3D platform like this. Thank you. Al.
Yeah, were you aware that Bonham Carter and Dianne also did a weights of evidence project over the entire Snow Lake camp based on Al Bales' 1 to 20,000, 1 to 50,000 maps? And what we did there is there's 10 conditions where, you know, what you need from the maps. But sorry. Okay.
Yeah, there. On? Hello? Yeah. So in this previous attempt, the only stipulation I made, because I gave them the conditions for where you should form VMS, is I told them they couldn't use training cells. Yes. And it was quite interesting. Obviously, it was a 2D exercise, but they actually defined the two massive sulfide horizons without knowing where the deposits were. Yeah. And then it went on the other side of the Richard Lake Pluton, and they could follow those horizons up towards the Ham Lake area. So it's interesting, this idea of using, obviously in 3 dimensions, using the training areas adds depth, bad pun, to your data set. But it's curious that it also seems to work quite well when you don't use a training area at all. You just use the criteria or the expert, sort of an expert derived method.
Yeah, I actually completed a knowledge-driven version of this project as well, just to compare the results. And in fact, they are pretty similar. You know, you generally know what features mineralization should be related to. And it's really, the weights of evidence analysis in this case helped identify what the appropriate weight should be, versus if you do a knowledge-driven approach, you're assigning the weights, so the weighting scheme is going to be different, but you're probably still going to see a lot of the same features highlighted. You're gonna look for faults, and you're going to look for the right geology, and you're going to look for plutons, and all of these things that are important in formation of a deposit. And really, it's something that we do visually when we do exploration. In the past, we primarily do this thing visually, but it's really just an easy way to combine all of these data that's difficult to process visually. And so yeah, it's not surprising that the same sort of features are going to be highlighted.
One comment, in the Bonham Carter study, they did do the weights of evidence or sort of approach, but then they modified that with an expert, expert-driven sort of information.
Yeah.
And that changed their model quite a bit. And one of the things they had was all of the VMS deposits were closely spatially associated with gabbro intrusions, and that was one of their highest, shall we say, associations. Now, if you go to the Chisel deposit, it's been folded and then cut by the gabbro intrusion that they were using as, distance from that intrusion was one of the, or other intrusions were criteria they were using to give a positive weight to proximity to a gabbro intrusion.
Right.
So I think what you've done is good. I think it would be to take it to an extra level, which would be to ask some of those questions,
Yeah.
Particularly with geology. I don't know about the geophysics, but with geology, it's important to know, is this a fault that's completely post-dating the mineralizing event? That could be 50 million years younger, has absolutely nothing to do with it. And so proximity to these features may mean nothing.
I agree completely.
So
yeah,
you have to bring that in.
I agree.
Any other questions?
Well, susceptibilities as a criteria, and I thought the pyrrhotite was a very vital importance of defining the conductance.
Yeah, I noticed
that.
yesterday in some of the introductory talks that pyrrhotite is part of the mineral assemblage, and I think this was thinking more broadly at that scale of the basin and the size of these alteration zones that are present. These alteration zones seem very prominent and large, and kind of looking at the big picture of mag destruction. I don't know how strong of an influence pyrrhotite is having on the mag signature at that scale. I don't know if anybody can comment on that or.
Well, wouldn't you try and model it within the sericite alteration? Because the mag, the pyrrhotite is mostly in the mass of the sphere.
I don't. Yeah. Hello. So the other thing I was going to ask is, did you use magnesium at all, or was it all just sericite alteration? Because magnesium is that's right underneath the deposit.
Yeah.
It's got to be one of the vital indicators. It's a hallmark of VMS alteration is magnesium from sea floor, seawater being precipitated just underneath the VMS. So and did you guys use magnesium, or did you just look at sericite? Because there's a lot of sericite lying around.
Right. We used the carbonate chlorite index and also the Hashimoto. The Hashimoto, that measures sericite and chlorite, does it, or some?
It's magnesium and potassium.
Yeah. So those two.
It's kind of a bulk thing, right? If you're measuring magnesium and potassium together, often when you're right next to the ore body lens, you're actually in plentiflora, which is there's no bloody
Yeah, I think it would be really interesting to do this same process at Lalor. You know, do some real detailed targeting where we could maybe see the differences between. Yeah.
And if you just
Yeah.
look at, if you're trying to lump the K2O, sericite alteration with chloride alteration, you're mixing two, one that's a direct vector and one that's kind of blank. Right?
Yeah, the outcome of something at this scale is going to get you in the area, I guess, versus maybe you shouldn't be